Okay, so those are some of the fundamental or very basics for image semantic segmentation. Now we look at into in the medical image domain, right? So we look at the problem, some of the evaluation metrics and data set, and some of the traditional methods, and also deep learning based method. Okay. So for the problem definition, so basically it's the same as the general semantic segmentation for natural image, right? So it's just the input is going to be not just the conventional RGB, but maybe different modalities as CT, MRI, or X-ray, right? So it's just different type of data, but the goal is still the same. Just to label each pixel in the image with a category label. Okay, so in the medical image computing, so the category label could be very specific, to the task or application, right? So if you're here, this example is doing the brain tumor segmentation, right? So the category label will be corresponding to different types of tumors, okay? But if this task is for just doing anomaly detection, right? So consider normal tissue or abnormal tissue, then maybe only have, binary category, right? You have a normal and abnormal, okay? And if the application is to do the organ segmentation, right? So you have this pancreas, kidney, liver, lung, etc., right? So you have the category label corresponding to different organs, okay? Again, so for semantic segmentation, here we do not differentiate instance. We only care about pixels, right? So if they are corresponding to the same class, then we'll just assign the same label for those pixels. We don't differentiate instance, right? Maybe have like lungs, you have left and right, but we don't differentiate them, okay? So this is very important for medical image computing. So you can consider this is like probably the most widely used task, right? So we can using, computer vision or machine learning technique to analyze and process 2D or 3D images, right, to achieve segmentation of human organs, soft tissues, and diseased bodies. Okay, so here I specifically mentioned it could be 2D or 3D images, right? So not like natural images, right? We mostly dealing with 2D images, right? RGB images. But for medical images, this MRI or CT, as we mentioned in the lecture, right, discuss different modalities of the medical data. They not only have the spatial, but they also have the slices, right? So that's corresponding to different cross sections of the body. So they consider 3D volumes, right? So we want to do volumetric segmentation. So the general process for medical image segmentation can be roughly divided into these stages, right? So first of all, once we understand the task at hand, right, we want to obtain the proper medical image data set, right, either for training or for evaluation, right? And the next step is once we have the data set, we want to do some pre-processing of the image, right? So just like some of the like you're doing natural image classification, right? Maybe you want to do the data whitening, right? Remove the mean, right? Divided by the standard deviation, right? Just to normalize the data. For medical image, there may be more, pre-processing step, like you want to maybe somehow enhance the contrast, maybe for some of the imaging modalities, right? So the raw data may not have a very sharp contrast. Maybe this may not be ideal for diagnosis of the diseased body or tissues. So it's kind of common to take some extra step to pre-process the data, enhance the contrast, or maybe even using some of the denoising technique, to remove some of the sensor noise, right? So once we pre-process these images or data, and we want to, consider or select the appropriate medical image segmentation method, right? And then once we figure out the method, we perform the segmentation, then we want to evaluate the performance, right? Typically, we have some standard metrics to evaluate the performance for segmentation, just like if you're doing image classification, right? We're using the accuracy, classification accuracy as the main metric to evaluate the performance. Okay. So first, let's look at the evaluation metrics. So these are the common evaluation metrics for medical image segmentation. So one is the DICE index, right? So this DICE index is used to calculate the similarity or overlap between two samples. Okay, so here for classification, for the segmentation task, the two samples will be considered as the ground truth segmentation map and the network predicted segmentation map. Okay, so we want to measure, right, the similarity or overlap between these two samples. Okay, predict and the ground truth. So here is a graph illustration of the DICE score. So basically, it's just compute the intersection of uni over uni. Okay, so here, this basically we want to compute, right, the intersection between the prediction and the ground truth, right? And on the denominator side here, we are compute the union of the prediction and the ground truth, right? So the reason we also want to consider the union is because let's say if your prediction is correct, right? You have a large overlap of the ground truth, but basically you are covering the entire ground truth, but you have some extra prediction there. Still, you have a large overlap, but the prediction is not as perfect as the ground truth, right? So we also have to consider their union, so that you want this intersection over union to be as high as possible. Okay, so that's the DICE score for segmentation. And also we have this Hausdorff distance. So basically this is a measure of the degree of similarity between the two sets of points. So the formal definition is that, it is the maximum distance of a set to the nearest point in the other set. So basically you want to measure the boundary of the two segmentations, right? How close they are. Okay. So because this Hausdorff distance is the maximum distance, right, of a set to the nearest point in the other set. So we want the maximum distance to be as small as possible, right? So in this case, you have a small maximum distance, which means these boundaries are very close to each other. But for the DICE score, right, so have the up arrow indicating the higher, the better. But for the Hausdorff distance, the lower, the better. Okay, so these are the two common evaluation metrics you will see for medical image segmentation. So a lot of time they using these two to as an indicator to evaluate how good is the segmentation algorithm. Okay. So for data set, there's actually a lot of medical data set. As this medical domain, we dealing with different modalities, right? Different applications. So depending on the applications and the data modalities, so here I list a couple of commonly used data set, right, for different tasks or applications, right? So the mostly noted is the this BRADS, which is the MRI database for brain tumor segmentation. So actually for the second assignment, programming assignment, we're actually going to use BRADS data set for brain tumor segmentation by using this MRI modality. Okay, so we also have like this kidney database to also segment the tumors for the kidney tumors, and we also have heart, eyes, and lung, etc. Okay. So this is just a couple of examples just to showcase some of the database. So this BRADS database, this is the MRI, right? So it has ground truths for different type of tumors, and the MRI, which is a volumetric data, has multiple slices and also has different modalities as well. So we have the T1 weighted, T2 weighted, flare, right? So as we mentioned, they are corresponding to different sequences of the MR images. So essentially, you can consider them as, when you process the data, right, you can consider them as channels, right? Like RGB, you have a red, green, and a blue. Here you have like 3 or 4 sequences. You can consider them as different channels, right, to process. Okay. And this is the drive digital retinal image for vessel extraction. So basically, you can consider this is like a binary segmentation, right? So just for the vessel extraction from the retinal image. So yeah, this white basically corresponding to the vessels. Then the black is considered the background. Okay. And we also have this whole heart segmentation. So for this 3D cardiovascular MRI, to diagnose this like the heart disease. So this is how the data set look like. And these are the ground truth segmentation map viewed in 3D. So because this is the volumetric data, right? So that's why we are able to view this in 3D, okay? And this is the example for the kidney tumor segmentation. I think I showed you, in one class, right, using the software to showcase this kidney this CT scans, right, from 3 different views and the corresponding, kidney tumor, right. So the green one indicating the tumor region. Okay. Okay, so those are just give you a quick glance of the some of the commonly used data set for different applications. And next, let's talk about some of the traditional methods for medical image segmentation, right? So before the deep learning become very popular, so people using the classic or traditional method to do the segmentation task. So these are a list of traditional method for segmentation. So one is the threshold-based segmentation. We can use in edge to do the segmentation. We can also consider regions to do the segmentation, right? So we group pixels, share the similar properties at regions to do the segmentation, right? And then we can using some of the maybe advanced theory, like using the graph theory, right, to build a graph to do the segmentation. Then we can also using some energy functions, right, to do the segmentation. So yeah, let's just briefly dive into these different classical methods, and then we'll move on. I'll talk more details about deep learning based approaches. So for the threshold-based method, right? So based on the name, right, we set a couple of set a one or a couple of threshold based on the the pixel intensity, right? So here, so this is not like a medical image, right? This is just a classic like grayscale image for the coins, and by examining these images, right, I think the first intuition is that maybe we don't need very complex or complicated method to do a good job for the segmentation, because the image here is very simple, right? If you look at the pixel intensity, right, we can plot their distribution, right? So these are the pixel intensity, their distributions. And if we look at this distribution here, it majorly kind of divided or grouped into 2 clusters, right? One is maybe a majority of the pixels will have the pixel value between, let's say here like 30, maybe 30 to 100, right? So in this range, right? Another major cluster is centered around, I think, maybe 180, right? So you have another group of pixels, right? So in this case, it will be easy, right? We can purely based on the pixel intensity and just set up a threshold, right? Maybe a decent threshold to separate these 2 group of pixels is around maybe 120, right? So you can just put a like a separation here, right? Then below in the threshold we consider one class, and above the threshold we'll consider another class, right? So here, if we're using this kind of thresholding method, this is actually the segmentation map we generate, right? By looking at this segmentation map, it's actually pretty good, right? We are able to identify this cone region, right? The circle region very accurately, right? So this is because the nature of the pixel intensity distribution of this particular image, right? Then let's go to this another example, which is the actual medical image, right? This may be an MRI image. By on the first glance, that we can roughly see that, right? More or less, you can see that there's a few groups of pixel intensity, right? So because you see there's a darker region, right, pure black, then you have maybe 2 or 3 different shades of gray, right? Though this may be a little bit bright, and then this is darker, and I mean bright, darker, and even darker, right? So you can plot this pixel intensity just like this, and maybe set up like 2 or 3 threshold so that you are able to differentiate these different groups of pixels, right? Here, we'll just select one threshold, right? So in this case, we generate a binary segmentation mask. As you can see here, right, we're able to generate a very rough segmentation map, right? You kind of identify some of the structure of the brains, right? But not to a very, a great details, right? So like we want to classify this gray matter or white matter, right? These fat tissues, right? We are not able to clearly distinguish these different classes, but overall, we still get a rough structure, okay? So you can see this capability of this threshold-based method is very limited, right? But for some of the simple cases, this may work, decent, right? So this is obviously a very simple approach we can try. And the second method is the edge detection-based method, right? So we can, using some of the edge detectors, right, to detect these edges, right? So here, we are able to, using some of the edge detector like the Sobel detector, or maybe, other Kenny edge detector, right? So, or maybe even more complex or advanced edge detector to detect the edges. Then we can, using some of the morphological filters, right, trying to connect these dots or disconnected edges, right, into more unified or coherent edges, right? And then in this case, we can also do the segmentation, right? So that's the edge detection-based methods, okay? And we can also have this region-based, right? We can group pixels into regions, then we can use that as the segmentation. So here has this watershed method as a region-based approach to do the segmentation. And we can also, using some of the advanced theory, like the graph theories, right? We can build the view the image pixels, right, to as these the nodes, right? And we can build the edges or vertex, and then using the graph theory to do the optimization so that similar pixels can be pixel with similar properties can be grouped together, right? So this approach, using the graph cut approach to do the segmentation. So those are we can consider those are the classic segmentation method. But now since the deep learning is kind of take over all the different tasks and the domains, right? So we have advanced deep neural networks can perform much better as compared to those classic approach, right? So for those classic approach, right? So we can consider those are handcrafted or hand engineered approach, right? So we're using some design principle, right? Using some of the prior knowledge, right, to build the algorithm to do the segmentation map. Now the deep learning, we are leverage data, right, to kind of use a data-driven approach to learn the optimal features from the data and perform segmentation or classification, Okay, so here, this is, I extracted from this review of deep learning based method for medical image processing. So they kind of categorize these method into different categories, right? Based on, this kind of taxonomy. So we have end-to-end, like fully convolutional neural network, and using GAN-based architectures to do the segmentation. So yeah, if you're interested, you can go to this review and see different types of or categories of method for segmentation. Okay. And here are just a couple of more detailed, right? So the tables, they list different network they use and different modalities for the task, and also the dimension of the data, right? Either 2D slice or this is 3D volume. Okay. So more to this. So if you're interested, you can go to the survey and check it out. Okay. So next, let's look into some of the classic or mostly widely used deep learning technique for medical image segmentation, right? So this is actually one method we looked at before in the very beginning when we talk about general image segmentation, right? So basically, it's just adapting the classifiers for dense prediction, right? So here, you're still using the CN network for classification, and you have this final predicted feature map for these 21 semantic classes, right? But the problem is that we need to have the original resolution as the input. So we do this kind of bilinear interpolation to increase the spatial resolution to the as to those for the input. And here we just more detailed kind of architecture of the network. And basically, if we isolate one prediction map, right, you can see on this particular heat map, right, what's the probability of each of the predicted or of each of the classes in this particular data set, right? So here for the Pascal, we have the 21 classes considering the background. Okay. And this UNet, which is the most widely used network for medical image segmentation, it achieved a very good result, and it's also conceptually very simple. So it, again, have this encoder decoder structure, and the reason called the UNet is because the author kind of draw this kind of architecture into like a U shape, right? So let me using annotators here. Okay, so if you just look at on the left, right? So this is called encoder side. Okay, let me use another color. Okay, so this is the encoder side. Okay. And on the right, this is going to be the decoder side. Okay, right? So we have this encoder and the decoder structure, right? So encoder is trying to, encoding the feature from the image and using, convolutional layers and pooling layers. Okay. And decoder side is trying to gradually upsample the feature map to the original input resolution. Okay. But one unique design of this unit is that if you look at this, right, you have this, gray graying arrow, right, which is kind of direct using the feature map from the encoder, right, kind of reuse the feature map from the encoder at the decoder side. Okay, so basically we want to combine the features from the encoder at the decoder stage. Okay. So the purpose is that we combine the spatial information from the downsampling path, which is this path, and with the upper sampling path to retain the good spatial information, right? If you think about it, right, so at this decoder in the initial, right, so the spatial resolution can be very small, right, because of the gradual pooling, and we kind of lost a lot of spatial information, right? And we are just doing some simple upsampling, right? You can using this kind of bilinear or bicubic interpolation to do the upsampling, but that information is very coarse, right? So you based on the limited spatial information, do the simple interpolation. You don't get much of the additional information from that. So how can we compensate, for those spatial information lost in the downsampling stage? That is, we can directly using, right? And we can, because this is symmetric, right? We can go directly to the encoder side and take that feature map and reuse them in the decoder side, right? For this particular layer, right? Hopefully some of the information lost can be bring back here. And so that when you do the upsample again, you have a much better representation, rather you don't using that feature representation from the encoder side. So that's their intuition, okay? And for this UNET paper, they also have another strategy to perform segmentation. So for their applications, or actually in a lot of applications in medical domain, like this microscopic images, usually they have very high spatial resolution, right? You may have, it could be like maybe 6K by 6K or even more, right? So it's a quite large image, right? So if you take that, high resolution image as the entire input, thus can be very computational expensive, may not be memory efficient, for the hardware, right? Maybe your GPU memory cannot fit this high resolution image. And another situation, often encounter is that the image may not have the same size, right? So you may have the images in this database has varying size, right? 200 by 200, maybe 500 by 500, right? So you have different like a image size. Obviously, what we can do is we can do a pre-processing, right? We can resize image to the same size, and then using that to feed into the same network. But what they do here is that rather, doing the resizing, that could, change some of the information, right? If you're doing if a small to resizing to a larger one, then you injecting some, introduce some of the noise, right? But if you have a larger resolution, then you reduce it, you lost a lot of information, right? So we don't want to, manually introduce these kind of noise due to this kind of pre-processing. So what they do is that let's just, do this kind of by tile, right? So all patch by patch. So here they have crop a large region, right? So this, if you look at this blue one, right, it have a blue patch here. So maybe let's say this image is 1000 by 1000, and this could be 500 by 500 patch. And we can using this input, this patch as input, and go through this UNET architecture and generate a segmentation map, right? And then we can go to a next space where maybe with some overlap, then do this again, okay? And a small things they also did is that, you can do this non-overlap patch, right? So maybe in the next position, my blue square is going to be here. So in this case, I will generate another segmentation map for this one, right? But the problem here is that, these edges may not be consistent, or you will see some artifacts, right? Because in this image, right, the context, these edges look at maybe mostly from here. But if you go from this large patch here, then the context for this boundary maybe only look at on the right side, right? So you may have some artifacts or inconsistency, along this boundary side. So what they do is that they also set up, when you predict this segmentation map, I don't use the entire one. I just take the center one, okay? So in this case, when you move over, you have some overlap prediction on the boundary side. So it's kind of like take the average of, one or two or even more predictions. So that's their tiling process in the UNET. And here shows some of the result for the UNET, okay? So this is for the ISPS cell tracking challenge. So they segment this cell. And this is some of the quantitative result using the unit as compared to some other approach. So that's the basic unit, which is operate in 2D space, right? So as we mentioned earlier, right? So a lot of medical image modalities dealing with volumetric segmentation, right? So we are dealing with multiple slices, right? So in this case, different slices, right? So we may have some correlations, right? So we also want to leverage the correlation between slices so that we are able to have a better representation. So analogy would be, you can consider, video processing, right? So video is not just a single image. I mean, you could do this slice by, image by image, right? If you're talking about video, you can do this frame by frame. You can still treat it this like a 2D processing, but as we know that the temporal correlation in video is very strong, right? Usually the neighboring frames in the video can give you a lot of extra information, right? So how the object moving, and they also share some redundant information, right? Some of the context. So in this case, if you leverage these neighboring information, then you may learn a better representation as compared to you only consider a single frame at a time, right? So this is similar for the volumetric segmentation, right? So we also want to look into the relationship among these neighboring slices. So that's why we add an extra dimension, right? Not just the kernel, not just operating in the spatial, but we also are operating in this kind of slice dimension. We can call this like a depth, right? In the slice direction. So basically you add an extra dimension of the convolutions, and you can build this 3D unit for volumetric segmentation. Okay. Here, just to give you a better idea, so I draw this not very good sketch, but hopefully you are able to still get a sense, right? What this 3D convolution look like, okay? So again, you can imagine, right? If medical image volumetric, these slices may be difficult for you to understand, you can view this, consider like a video processing, right? So this is the video frame, right? So we have 1 to maybe 100, right? We have 100 frames, right? So we have height and width and a channel C, right? C here, if RGB images, we have 3 channels, right? RG and B. So the typical image classification, we just have a K by K by C, right, convolution to operate on this single image, right? As I mentioned, right, so we want to also capture this temporal correlation, right? So we want to add extra dimension of your kernel so that we can take multiple frames at the same time to model that spatial and the temporal relationship, right? So now we're just adding an extra dimension of D, depth, right? So here, for simple explanation, we consider 3 frames at a time, right? Maybe your spatial can also be 3, K can be 3, right? 3 by 3 spatial, and by 3 frames as the temporal, right? So we can do this kind of matrix dot product, right? We can generate a value here, right? You basically just, moving around here, then you generate a feature map indicating as the blue square here. You have a 1 feature map, okay? So this is 1 kernel, right? So if you have another kernel, right, you do this, you generate another feature map, right? Maybe a different color, okay? And so the next step is, if we look at still consider the same blue kernel, right? So we can move into the next position, right? So here we consider 1, 2, 3 frame, right? The next position we can move is from 2, 3, and 4, right? We move along the temporal dimension, right? So we can do the same, and we generate another feature map where we indicating this is indicating here, right? So we do this kind of correspondingly, right? So we indicating this is like corresponding to the temporal, right? So the feature map you generated is still like a 3D space, right? You have a spatial, you also have the temporal. So in this case, you can build another 3D conv layer and do this on this feature map, right? So here, the initial, we are operating on the original input video, okay? So that's how this 3D conv is operated. So basically, just consider an extra dimension of time, right? For medical image, you just have an extra dimension of depth, right? Indicating, different slices, okay? Hopefully, this will help you understand this 3D unit, how it will operate. Okay. Do you have any questions regarding this?
Are all the convolutions 3D, or is it only for the input layer?
So in this case, this conv is going to be a 4D tensor, right? So, usually we don't we don't say the channel dimension, right? So this is going to be default, right? But if we want to explicitly write out, right, it's going to be 4D tensor, right? Channel, spatial, and the depth, right? As I mentioned, right? So if you're moving, this, if you only consider this, the blue kernel, let's just consider one kernel, right? This blue one, right? You generate feature map here, right? But if you're moving to the next position, you operate it on 2, 3, and 4 frames, right? You generate another frame. You can consider this is still like corresponding to the frame dimension, right? We want to match this kind of depth dimension, right? So this is the first corresponding to the first frame. This is the second frame. This is third, etc. Of course, you need to do some padding in order to match the same 100 frames, but the idea is that you still want to maintain this kind of spatial and the depth or temporal dimension. So here again, in the second conv layer, 3D conv layer here, you're still gonna apply these 4D tensor, right? Because you still have this kind of depth dimension. Okay.
Okay, thank you.
Yeah, no problem. Okay, so that's the 3D unit, and this is another network called VNet. So I think they are just trying to distinguish this kind of naming, and they kind of draw this image like a V shape, right? So before you have a U, here they purposely like draw like a V shape. So as you can see that most of the operations or component are very similar, right? So you have a conv downsampling on the encoder, and you also have the upsampling stage on the decoder side, right? You also combining some of the feature map to the decoder side, right? One thing that is different from the VNet, the unit or 3 unit, is they also consider this kind of residual connection, right? Before, if you look at unit here, they don't have that, right? So they basically just conv, pooling, right, and up convolution, right, doing the upsampling, ReLU, etc. So here, basically bring this kind of residual connection in the ResNet into the picture so that the learning can be better. So that's the VNet. Okay, so here are some of the quantitative result, right? They're using this is for segmentation. They're using the average dice, right, Hausdorff distance, to measure the performance and do the comparison with other methods. And we also have other couple of UNet variants, right? Because UNet is very simple and successful. So people try to build upon UNet and trying to modify it or maybe improve it, right? So here it's just this UNet++. Basically, you can see some of the ideas or maybe inspired by like a DanceNet, right? So the DanceNet, you have different skip connections, right? So here they kind of have multiple stage skip connections. Here you can go from here, then go down to the middle. You can not necessarily you have to wait till the decoder side to do the upsampling, right? So in the encoder side, you can also upsampling, right? Essentially every downsampling stage in the encoder, you can again do the upsampling here, right? Go back to the original size, right? Yeah, this is kind of like a multi-level or multi-scale learning, so that the learned representation hopefully can be better, right? Because after all, we're talking about class segmentation for each of the pixels, right? We need to learn those contexts very well. Okay. So those are that's the structure of a unit plus plus. So they also do this comparison, right, with the original unit and other variants like the wider unit and their approach, right? So this is for the binary classification, and they are able to have better result, right? Especially for this particular example, right? So this unit and wider unit have generate some the false prediction, right? So this not supposed to be maybe some of the diseased tissues, but they make this false prediction. But UNet++ is able to maybe capture more context, so remove these kind of outliers. Okay. And this is just some of the quantitative result to indicating their result. Like if they have deep supervision, right? So you have multiple scale, you can do the upsampling in the encoder side, right? So they call this a deep supervision, right? Not just at the end, you have the ground truth to supervise the prediction, but at multiple stages, you can supervise the learning. So they show this, this deep supervision is able to help in terms of the segmentation performance. Okay, so another variant is the attention unit, right? So when we talk about this attention mechanism and talk about the transformer architectures, right? So we kind of introduce the attention mechanism, what this attention mechanism is used for, right? So basically, this attention is trying to highlight, right, some of the relevant regions or activations during the training, right? So we can using attention mechanism to weigh different parts of the input or feature map, right? So we only pay attention to those are relevant or maybe important, right? So basically this soft attention mechanism is that we can weigh different parts of the image, and the relevant parts of the image will get large weights, right? And less relevant parts will get smaller weights, right? So this is intuitively makes sense, right? We want to pay attention to the important or relevant parts. And during the training, right, the weights can be trained, right? The weights, essentially those parameters can be optimized during the training, right? So we are not assigning a hard attention, right? Hard attention means you can fix some of the tension, but that may not be ideal, right? So we want the network to learn what is the optimal weights for different parts of the image, right? And so basically it will add weights to the pixels based on the relevance. And let's look at this attention unit, right? How can we add an attention to the unit structure? So here again, I'm just put the unit structure here, right? Just to for illustration. So this is the vanilla unit structure. So basically, it will combines the spatial information, right, from the downsampling path, which is the encoder, with the upsampling, right, the decoder side, right, to retain the good spatial information, right? So we do this symmetrically. But this process may bring along some of the poor feature representation from the initial layer of the encoder, right? So if you look at this initial layer, right? So as we mentioned, right, initial layer, it only learns some of the coarse feature representations, right? Edges, corners, right? Those fundamentals, the basics features from the images. So those feature representation may be very coarse, right? So if we combine them, right, we concatenate these features in the decoder side, right, they may introduce some of the poor feature representation. This may affect the final prediction, right? So we want to kind of using some of the attention layers or attention mechanisms, right, to suppress some of the activations that may not be relevant, right? So we only pay attention to some of the regions or relevant activations that are useful for this particular layer. So they build this or injected this attention component or module, right, on each of these upsampling layer, right, to determine, right, how should we better incorporate this features from the encoder side, right? Which part we have to focus when we combine with the decoder feature, right? Rather just blindly, use them all and simply concatenate them and do the follow-up process. Okay. So this is a detailed kind of architecture of this attention unit, right? So they have different operations and this indicating different feature map at different layers. And this is the graphic illustration of their attention unit, right? So how the attention is being generated, right? So this gated additive like attention gate, right? What's the structure of this attention gate is built? So maybe we can using an example, right? Actually, a concrete example just to go through this attention gate and see how this attention weights are being computed and how the attention weights are used to weigh those different weigh the pixels from those feature maps from the encoder. Okay, so if you look at let's see, can remove this. Okay, cannot remove this. So can you see my pencil here? Are you able to see where I'm indicating like XL?
Yes.
Okay, good. So the XL is basically the feature map from the encoder, right? So coming from the encoder, okay? The G is the feature map from the decoder, right? So before we talk about attention unit, right? The unit is basically simply concatenate them together, right? So here the attention unit is that this XL from the encoder needs to go to this attention gate to weigh those pixels in this feature map and combine with the decoder feature, okay? So that's the XLG, okay? So here we have the G, right? So that is here, and we also have the XL, right? XL is from the encoder side, right? So let's see how this attention gate works. And for some of the networks, right? So maybe the spatial resolution will be different, right? So I mean, we can make it same, right? The height and width, right, to be the same or symmetric. But even if you have a different spatial resolution, we can have some of the process to make it the same, right? So in this case, so these two sets of features, right, G, XL, is go to this 1-by-1 convolution, okay? So the 1-by-1 convolution with stride 1, right? So basically 1-by-1 convolution does not change the spatial dimension, right? So take like 1-by-1, just one pixel at a time, and you can specify how many 1-by-1 convolutions you can use, right? If you have 128, you end up with 128 filters, right? So this number of filters corresponding to the channel dimension, right? So in this case, we'll generate a 60 by 6 by 128 feature map, right? The reason here is that because we're gonna do some concatenation or operation, adding them together maybe later, we need to have a same dimensionality in order to perform those operations, right? So we have a fixed or have the same channel dimension. And if we look at the spatial size for the X, right? So it's kind of double the size compared to G. So here now we use a stride of 2, right? Effectively, this will reduce the size by half, right? If we have a stride of 2. So you will see that we'll end up with a feature dimension of 64 by 64 by 128, okay? Now we can adding them together, right? So we can add these, feature maps together, right? To this is not concatenation, right? Doing the addition, right? So which means we adding the value of each position. Okay, so essentially we still end up with a 64 by 64 by 128 feature map. Okay, but the idea is that the aligned weights or these the values in this feature map will get larger, right? Unaligned weights will get relatively smaller, right? So if these features are aligned, right, maybe this pixel corresponding to the tumor region, right, you align them together and you adding them together, then you get a larger response, right, corresponding to that specific pattern. Okay, so we get a larger value, or some of the doesn't align, we may get a smaller value, right? And now we can go through activation function, right? So we can maybe go through a sigmoid, or maybe we can using another like a 10H or some other activation functions. So sigmoid here is basically you want to scale them into between the value of 0 and 1, right? So this can be considered as a attention weights, right? And then we can adding another 1-by-1 convolution, right? But just using one filter here, we kind of effectively reduce the channel dimension, right? So before we have 128, now we using only one filter to reduce into 64 by 64 by 1, right? Basically reduce into one channel. Okay, so then we can also scale this the weights, and maybe using softmax and to normalize it, and we can reshape or do some interpolation to 128 to 108. And then we multiply these attention weights with the XL, right? So which is the feature from the encoder side, right? So this matrix here, right, 100 by 128 contains the attention weights. Okay, so we multiply these attention weights with the original feature map. So we know that some of the regions, if we have a larger attention weights, then we pay more attention to that, right? If we have a smaller attention weights, then we pay less attention to those pixels or parts. Okay, so that's the attention mechanism, right? So if you go to this figure here, right, so you have this attention map here, then you multiply it with the feature map from the encoder side, and you get this weighted feature map. So then you can combine with the decoder feature G. Okay, so this is the attention mechanism from the attention unit. And this figure shows you how this training process, right, how this the attention map is gradually changed over the training process, right? So this horizontal, right, different images, right, shows the images and the attention map overlaid on this image, original input, and how this attention map changed over time, right? So the different training epochs, 3, 6, 10 to 150, right? Maybe 150 is the end of training, right? So this is their final result. So as you can see that in the very training beginning, right, the attention weights is not very good, right? So you can see there's high response or attention weights all over the place. But gradually, right, so you can see that these attention weights all focused on some of the specific organs of the body, right? So this may be focused on the pancreas, kidney region, right? So spleen region, right? So they all kind of very focused on these parts. Rather, you have a large region, right? All have a large attention or response here. So that's how they show, right, how this attention map makes sense, and how this is going to evolve during the training process. And they also show some of the result for this, pancreas segmentation, and do some comparisons with unit, right? So the unit is here corresponding to C, this image highlighted by the red bounding box, and D is their attention unit model prediction, right? This green box, and B is the ground truth. Okay, so this is the accurate, annotation of the pancreas. So basically, these arrows can highlight, right? So using the attention mechanism, the prediction can be more accurate, right? So these boundaries are more accurate. So if you compute the Hausdorff distance, this will definitely smaller as compared to this one that is generated by the unit model. Okay. So this is the quantitative result, right? They also using the dice score to measure the performance, and using the attention mechanism in the unit structure give them better performance as compared to the vanilla unit. Okay, so since we kind of realized, right, the attention mechanism is very effective, right, for medical image segmentation, right? It's kind of way different pixels or regions so that some of the important regions can be highlighted so that the prediction can be more accurate. So along this line, right, then we can consider using the transformer, right? So we can specifically build this kind of long range correlations, and also using the self-attention mechanism, right, to learn which pixel or which part are important for specific prediction. So in this work, this transunit architecture, they also consider the transformer, the layer or some of the blocks, right? So actually this is a hybrid network, right? So if you look at the architecture here, so the input is this maybe CT image, and go through this CNN network, right, to extract some of the features, and then using the transformer layer, right, to build this kind of global correlation, for the CNN features, so that the global correlation can be modeled better with the transformer layer. And then similarly, they have this decoder, right, to gradually upsampling the feature map and eventually generate the segmentation map. Okay, so the idea or the effectiveness come from the transformer layer to build a long range or global correlation as compared to just using the CNN network. So they are able to achieve better performance as compared to some of the CNN baselines like UNIT. Okay. So just to refresh your memory, right? So last lecture, last week, we'll talk about the transformer, right? So this is the basic structure of the transformer encoder, right? So for image, we divide them into patches. And for each of the patches, we can do some linear projection to generate kind of like a feature embedding for each of the patches. Then we go through this transformer encoder, right? So this is the transformer encoder, right? So we have multiple components, mostly notably the multi-head attention layer to model the correlation between the input. So in their case, right? So once you have these CNN features, right? So you have all these hidden features, right? Then you can consider these are coming from, instead of just directly operating on the patch, they're using CNN to extract the initial features, right? Then using this as an input, go through this transformer encoder layer, which is here, okay? And this trans-BTS for transformer for brain tumor segmentation is also another work which is using the hybrid structure, right? So you also have the CNN network, also have the transformer encoder to model the global correlation for segmentation, right? Again, the general architecture still follow this encoder decoder structure, right? So you have the encoder part, you have the decoder part, okay? The way they injecting the transformer is, again, after the CNN, you have the transformer encoder to model the global correlation, then using that to feed into the decoder. The difference compared to the trans-BTS and the previous transunit is that this is a volumetric based approach. So for the transunit, it's a 2D approach, right? Basically, they operate on individual slides, right? They are not taking multiple slides at a time. So basically, they do this kind of slice-based segmentation. Take one slice, do the segmentation, then go to the next slice and do the segmentation. But for this trans-BTS, they're using 3D CNN, like 3D UNet or VNet structure, right? You take multiple slides and use multiple slides as an input, right? As you can see here, you have an extra dimension of D here. as input and go through this 3D CN to extract the spatial and the depth features, and then go through this transformer layer and go through this decoder side to generate the output. Okay, so that's the one fundamental difference as compared to the transunit. Okay, so here I'm listing these two fundamental difference. Right, one is slice by slice. The other is 3D volumetric approach. Okay, you can think of this like 2D unit and 3D unit kind of differences. And another is the transunit, which is 2D version. They use the pre-trained model because they are doing 2D, right? A lot of transformer models or CM models, they can using the pre-trained model that may be trained from ImageNet or maybe trained from natural image segmentation, right? The cityscape COCO data set, right? So they are very large. So they can leverage these pre-trained models in their approach. But for the volumetric approach, right, this trans-BTS, there's no like large scale pre-trained model, right? At least we don't have this kind of volumetric data in the natural image. But one possibility is we could using video model, right? Maybe using the 3D CM trained on video classification or video action recognition. We can do that. But in their approach, they didn't use any of the pre-trained weights, pre-trained model. Basically just train from scratch based on the data set at hand, right? Maybe just Brett's data set train from scratch. And so these are the two basic differences between these two works, okay? And later there's also this trans attention unit. So, based on the name, you can see that, right? So the more or less just using some multi-level attention guided unit with transformer architecture, right? So basically just a attention unit combined with transformer encoder, some of the component in their framework so that they may able to learn this local and global information better so that the segmentation accuracy could be improved, okay? So these are the works for the segmentation. So hopefully you get an idea for medical image segmentation. And yeah, so this is all for the segmentation. And for the next lecture, we'll talk about generative adversarial network and its application for medical image computing. Okay.